This is the third tutorial in the transient analysis series, and we'll utilize the same simple RC circuit utilized in the first two of this series. In this case, the emphasis will be directed toward plotting two or more variables on the screen and how to scale for different values. So we start with the circuit as shown here, as it was left in tutorial the transient analysis number 2, with the RC circuit excited by a sinusoidal function at 1 kilohertz. And we're going to look at the transient analysis again. So if I go up here to the grapher, click on transient analysis, and look at the outputs, I'm going to set the initial condition to 0. I'm going to use that option with a maximum time step of 10 microseconds and look at the output. Well, in this case, it's already been set. I could start from scratch and set them all over again, but I don't think that's necessary. The first one, case here is I'm going to show V1 and V2. Now, V1 is the input voltage and V2 is the output voltage. Also, I'm going to simulate the time step that has been set for a time duration from 5 milliseconds to 10 milliseconds. So let's see how we obtain the results in this particular case. So you see here from 5 to 10. The reason I did that is so we could look at it in the AC sinusoidal steady state, so we don't have the transient to get in our way. So this is really steady state AC. Again, even though it's called transient analysis, that particular option can do both transient and steady state, and we're looking at steady state. Now, because the voltages, the input voltage of 100 volts and the output voltage, which is somewhat smaller, appear on the same scale, there is not a serious problem necessarily unless we want to make some precision measurements. If we want to make some precision measurements, we can expand the output voltage so it occupies a much greater range. As a matter of fact, we could go back and change this where we're going from minus 100 to plus 100 and expand both of them at the same time. But at least we can see both of the waveforms in this particular case, even though they one is much smaller than the other. We can see them both, and we could probably measure, even though the accuracy might be degraded a little bit. However, let's get out of this one and go back to transient analysis again. And this time, let's assume that we want to look at V2, which is already there. I'm going to get rid of V1, the input voltage. I'm going to remove it, and instead I want to look at the current around the loop. Now, because this is a series circuit, the current in several components is the same, so it really doesn't matter which one I look at. I'll just arbitrarily pick I of R1, the current through R1, and add it over here, and I'll hit simulate again. Incidentally, I think I'll also change the background to white. Now, I mentioned in an earlier tutorial that you could do that by clicking on graph and then toggling on black and white colors, but there's also a toggle here. If you click on this black background button here, you will get the white in the background, and you can toggle it back if you so desire later, but at any rate, I'll use the white in this particular case. I can also widen the trace here, but I'll leave it as it is. Now, this is the output voltage, and it's showing up as something around 16 volts or so. I don't remember the exact value, but notice that what we're seeing for the current through R1, we see that down here, that the green curve is the current through R1. We can't even see it. And the reason is that the current, because of the size of the components in the circuit, the current is down in the milliamp region. The voltage is way up here over 15 volts, but the current is down. If you make a calculation, you'll find it's well under 1 ampere. In fact, it's around 100 milliamperes. So we can't see it. So we have to change it somehow in order to see that. Now, if I go back and just plot the current only and not plot the voltage, you can show it that way. In other words, create two separate graphs. But let's see if we can't show them both at the same time. Now, this process is a little bit tricky. When I leave it for a while, I always have to go back and review the process again. And by the way, I have clicked on the grid already. That was set up before we started, but just to review that process, that button here puts a grid on it and removes the grid when you click on it. If you left click anywhere in the area around here, double click. Finally got it there. I didn't click fast enough. This particular window opens up. Now, it has all the different options that you would like to have for a display. First, I'm going to look at the traces. Now, it is set on trace label B of 2, which is red. We can click on this button here and go to the second trace, which is I of R1, i.e. the current around the loop. So I've set it to I of R1, and I want to come down here and set that to the right axis. Now, it doesn't show up anything yet. We have set I of R1 to be the second trace in green, which you see here as a very small amplitude as far as this scale is concerned. And I made it the right axis, and I hit OK. So when you hit OK, it comes up to a larger magnitude, as you can see. Now, the next thing I'm going to do is double left click again in the area and go over to the right axis. Once again, hit right axis. I enable the right axis, and then I come down here to auto range. Before I click it, let me run through that. And by the way, I should also put a label over here. I'm going to call that current, and I'll just put capital A to represent amperes. We could write out amperes, but I'll leave it as capital A, the standard SI abbreviation. So the current in amperes is here. I've enabled it. It's a linear scale. That's what I want. And next, I'm going to click on auto range and then OK. Well, look what happens. The green curve comes up to a sizable magnitude on scale. And over on the right-hand side, we have current in amperes. And you'll notice that the current ranges, well, it's a sinusoid, so the positive peak should equal the negative peak. It appears to be something greater than 100 milliamps. We could measure it, but I'm not going to do that now. I'm just going to stay with the two waveforms. And you can actually go in and manually change the scale as well, but this should be adequate for most purposes. So we have the red scale as the voltage, and we have the green scale. I may have misrepresented what I said earlier. The green scale is the current scale, and it's a little less than 100, around 100 milliamps roughly. And the red scale is the voltage scale. We have both of them. And this has given us a much larger representation. So if I wanted to, I could measure things like the phase shift between the voltage and current for steady state AC. If I wanted to do that, I would recommend going back and plotting it over a much shorter time interval so that the scale stretches out. So, for example, we could measure it even over 1/2 cycle, and using that time basis, we can measure what the time here is and represent that as a fraction of the time for one cycle. and get the amount of phase shift. But I think the point has been proven in this case. So by using the process of steps that I showed, you can actually activate the right scale. And by the way, I have, because of the fact that this was originally labeled as voltage and current, I might want to go back and change that. So if I want to click again and go back to the left axis, I want to get rid of current. And as a matter of fact, I should call that the capacitor voltage or output voltage. Let's call it output voltage. It is a capacitor voltage, output voltage, and click OK on that, and you see that has been changed now to output voltage. So this concludes this particular presentation, which shows how to set the right axis and obtain a better representation of the variables in the circuit.